coming out. Yeah, like she said, I'll be talking about DNS-based authentication by named entities, how it interacts with the CA system, and see if we can't fix some things. Just out of curiosity, who here has heard of DNSSEC? So nice, pretty good size. And what about DANE? Yeah, a lot less. All right, great. Well, this is gonna be a good starting point. So, who am I? I'm Tony Cargile. I'm a security engineer at ISEC Partners. I get to carry out a lot of application infrastructure, pen tests, anything ranging from white box to black box, mobile infrastructure, web app, you name it. Before that, I went to school at UT in Austin with a degree in computer science. And before that, I was programming in web application and configuration management environments. So what am I going to be talking today? Well, I'd love to just jump right into DANE, but unfortunately you can't really do that with a good primer in DNSSEC, and you can't talk about DNSSEC without the problems of DNS. So, and then after that, we're going to talk about, what's the purpose of DANE, what is it fixed, why is it there, for those people playing security bingo. We'll talk about Heartbleed, and then we'll end up talking about some potential issues with DANE. So, what is DNS, Domain Name System? Well, hopefully this is a refresher for most of you, otherwise this talk might not go so well. But DNS is basically just a way for us to resolve www.bank.com into an IP address. Client sends a request out with an A record type and gets a response back with an IP. So what's some of the problems with DNS? Well, it's old. Bind was created in 1984. Sadly enough, that was before I was born. The ROCs finally got ratified in 1987. So back in that time, security was a blimp on the radar. No one was really worried about DNS spoofing, cache poisoning, or any of the issues that we're having to deal with nowadays. So let's talk about the first issue with DNS, and that is that it provides no integrity, no confidentiality, no availability. So it's pretty trivial to spoof DNS. So say a hacker gets in the middle of a client making a request to the DNS, or to a website, making the DNS request. If we can intercept that, we can just simply reply back with the IP of our malicious fake site, and the client simply goes there. There's no guarantee that that information that that client is receiving is legitimate information. So the second issue is DNS cache poisoning. And this is a little bit more sophisticated attack. What this is doing is, instead of just replying back to the client saying that the legitimate site's IP is actually our malicious IP, we're actually sending a response back to a caching server. And then that caching server is then going to send that response back to anybody that asks that server. So what this is going to do is our attacker is going to send a request to the DNS caching server, then it's going to spoof a response back saying that, www.bank.com is actually 1337, and then now anybody who sends a DNS request that goes through that caching server, well, now it's going to respond back with that 1337 for as long as that TTL of that packet. So originally it was pretty trivial to do this. All you really had to do was match the query ID of the DNS request to spoof a DNS response. So in that query ID is only a 2-byte identifier that you could just trivial brute force. So the original solution was to just make the TTL extremely low, but that really wasn't a solution when Dan Kaminsky came along and showed in 2008 that he could just use a bunch of different subdomains, just brute force subdomains, randomized subdomains, and he just got around that TTL. And that was an issue for a while. Finally, the real issue was port randomization. Basically, when a request goes out, it actually goes out on a random port, not on port 53. So you can't just send a forged response to that port. You have to also guess the port and the query ID now, which gains a ton of entropy. It's a lot harder to brute force, but it's really not a perfect solution. If you can get lucky, then you can still do DNS cache poisoning. So then there's some other issues with DNS. There's really no validity checking. So isecpartners.com, you can actually register a domain of onesecpartners.com. You don't have that same validity checking that you would if you say went to get an SSL certificate for onesecpartners.com. Hopefully you get denied, but we'll see later on that that's not usually the case. And then also, of course, we're relying on DNS, so DNS servers are another issue. There's been some compromises in DNS protocols, so that's always something we need to take care of. So now that we talked about kind of the issues with DNS, we'll jump into DNSSEC. And this was really created just to answer the problem of DNS not having any security by default. So what is DNSSEC? DNSSEC provides origin authentication of DNS data. It provides authenticated denial of existence, and it provides data integrity. Notably, it does not provide two things: availability and confidentiality. So we're going to go ahead and talk about how it does this. It's kind of a bold statement to just say, complete data integrity, complete origin authentication, but we're going to show how it does this. So first of all, it adds a few record types. So it adds this RRSIG record type, which is going to hold the signature for every record in the DNS zone. It's also going to hold a DNS key, which is going to be the public key for the signature. It's going to have INSEC, which I'm going to go into a little bit later about for use for denial of existence. And then you use your delegation server. So I'm going to go over these a little bit more in depth in a few minutes because this is really important for DANE. But what this essentially does is you have a zone which you have each record type in that zone. You're going to make you're going to sign that zone with your key signing key. Your zone signing key, and that entail will be provided to. That signature will be provided to anybody that makes a request out to, say, an A record. You're going to get an associated RRSIG record with that, and then the public key for that will be stored in the DNS key, and then to provide a chain of trust, we also use a delegation signer, a DS record type, to specify our parent domain. So this might be a little bit confusing. This might clear it up a little bit. So what we're doing right now is say we're looking to sign www.mybank.com. Well, mybank.dom will sign that certificate using its public key private key pair. And then when it does that, it will publish its public key also to the .dom domain. And this domain will hold that DNS key, and then it will in turn sign that key with its private key. And then publish its public key and also push it to the root domain. And that's where this entire chain of trust lies, is in the root domain. So we would pin on the public key for the root domain. So let's just go ahead and jump into what this actually looks like tangibly. So this might be a little bit small for the people in the back, but this is just going to be a Wireshark capture of a request sent out. So it's pretty simple. We just have a type A record request to DANE, good.dane.verisignlabs.com. Looks like a normal A request. There's just one flag that's been changed that says it's DNSSEC approved or capable. So then when we send this request out, we get a response back that looks similar to this. So one, we get a response back with our type A address, just like we would normally see if we sent a request out. But then we also get this RRSIG back, which I said was a signature for that type A response. So in here, it specifies a few things. It specifies the algorithm that we used. It also specifies the signature, of course, and the signer's name. So that now when a DNSSEC client wants to verify this, they can then go look at good.dane.verisignlab.com DNS key, and then they can perform a chain of trust command to make sure that the request that they just received, that type A record, is actually coming from the server, it hasn't been modified, and it's actually there. So hopefully that was just kind of a refresher, but so there's some issues with DNSSEC, right? But they also provide some really good things. Like I said, it provides authorization and integrity. So no more spoofing, no more cache poisoning, which is a huge benefit. Like I said, it's still an issue that we're having to deal with right now. Notably, though, it doesn't provide confidentiality. So anybody that's sniffing on that network will know where you're going. There's some other solutions that take care of confidentiality. If you're interested in that, take a look at DNS Curve. That's a pretty cool solution for the confidentiality of DNS records, but it's something that's a little bit out of scope for this talk. So how does DNSSEC take care of DNS spoofing or DNS caching? Well, anytime an attacker is going to try and man in the middle that DNS connection and modify it, he's not going to be able to sign that RRSIG with his own private key because it wouldn't match up with the DNS key that's on the fake site, or on the legitimate site's DNS server. So if an attacker was to man in the middle and give its own, the DNSSEC validation would not happen, and the attack simply fails. So one thing I kind of glossed over, but DNSSEC provides denial of existence. So if you send a request out to doesnotexist.google.com, it'll actually come back and say that domain doesn't exist in our zone, and here's proof of that. And it does that by sending back an INSEC record type. So what does this look like? So we send a request out to write.net with a domain that doesn't exist. So I think I put e.write.net right here. What this actually does is it sends back a request saying that doesn't exist, and I can prove it to you because there's, in this one it shows there's 256cns.ripe.net and elearning.ripe.net, but there's no e.ripe.net. So I don't know if you can kind of already put the pieces together, but this allows you to just do simple zone enumeration. So if you were able to just go in and be like, all right, is there a.ripe.net? And they're going to tell you anything before and after A, and then you can just go down the line and you can figure out all of the domains, the subdomains in that zone. So the answer to that was a modification of the DNSSEC RFC, which introduced INSEC 3. And what this does is it just provides hashing before it does any of the checks of the zone. So here we send in, this is actually going to my domain now, e.tonycargile.com. Now what it does is it hashes that subdomain and then checks against a hashed list of my subdomains. So now it's saying, okay, DMC blah 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 .tony.cargile doesn't exist, but in the hash before and the hash after it does exist. So what this does is this allows us, we would now have to crack all the hashes in for this zone to be able to enumerate it. So that does provide some security, but this is just a SHA-1 hash. And so a big negative is people are saying that with a big enough computer you can just go ahead and crack all these hashes and you can still do enumeration on DNSSEC approved zones. So, and it's like, well, zone enumeration, what does that really matter? But I've seen some pretty creative uses of DNS records, like TXT records that hold passwords in it, or information about internal networks inside of zone records. So a DNS zone enumeration is a pretty powerful thing. So another thing, when we look at a DNSSEC record response, it's containing a pretty sizable hash of that record type. And so when a simple request of an A type with a spoofed source IP would result in a response to that IP of a very large data chunk. And so we could actually use this to do DNS amplification attacks for DDoS. We've already seen this in the wild a few times of using DNS to do amplification, and DNSSEC would just make those even more powerful because that's quite a bit of information coming back from a small response. And then finally, like I talked about, there's a chain of trust, right? So we're using the zone signing keys and the key signing keys to validate the record, and then we're validating each step of that chain until it gets to that root zone, and we have to pin on something. So right now we're pinning on the root zone, and that's owned by the government. So that's owned by IANA, and so take that as you will. Some people say, well, that's a really good thing. Other people say they don't trust it. So that's just more of your interpretation of that. And then finally, the biggest problem with DNSSEC is the implementation. So, DNSSEC obviously has been out for a while. The root zone finally got signed on 2010, and the .com zone got signed in March of 2011. So it's been around for a little bit, but as you can see with this graph, what we're looking at here is a chart of DNSSEC implementation over the entire zone. So this top one's .edu. That one's not as complete, but this bottom one, this is the .net and the .com zones. .net being in the blue in the top one. And if you look over there, right now we're peaking on the .net at 0.5% of all .net domains are actually implementing DNSSEC, and even lower than that, .com right now is at about 0.3% of all .com domains are DNSSEC approved or signed. And a pretty funny little site you guys can go check out is DNSSECnameandshame.com, and it will actually, I don't know if you can see that, but it'll show you the Alexa top 25, and not a single one of those signs their records with DNSSEC. You can just put in name after name after name to the site, and none of them validate DNSSEC. So I'll go into a little bit of this later of why this is, but needless to say, that's a huge negative when we have the security out there, but no one's adopting it. So now that we got a good primer on DANE, yeah, go ahead. Got a question?
I was going to ask, does it do the same functionality for the inadder.arpa side of the tree?
You know what? I haven't actually checked that. So.
So I'm asking PTR right here. Right?
Yeah.
Totally different infrastructure.
My thinking, if I had to guess right now, is that it should, but I haven't actually verified that. If you want to get with me after this, I can give you my card. I can go check that real quick and let you know. All right, so after we got a good briefer of DNSSEC, we can finally start talking about DANE. So what is DANE? DANE is a way of being able to do certificate pinning using DNS records instead of using SSL certs. PKIX certs. So it's built completely on top of DNSSEC. We use all of the integrity and authorization of DNSSEC to verify our DANE records. And its goal is pretty simple. It's just take away the reliance on the certificate authority and put that on the DNS server. So it does this with one simple record type. So we have a TLSA DNS record type. And what that's going to do is that's going to hold the signature of the SSL cert that you're about to receive from an SSL server. So you can actually check this by just doing a dig for a TLSA record type, and then it goes in a format of underscore the port that's going to be running on, dot underscore the protocol that's going to be running on, dot the domain. So if you wanted to see the certificate that you're going to receive from good.dane.verisignlabs.com, you would just make a TLSA request to that URL that's up there. So what does the TLSA record type actually look like? It's actually pretty simple. It's just got 3 different fields plus the actual signature. I'm going to go over these fields, but they're certificate usage, the selector, and the matching type, and then the signature. So first of all, what's that selector? So we can actually say that we're about to specify a full certificate, or we're going to actually specify the subject public key info. So we can either pin on the full cert or on that just that simple field. We can use we can do a one-for-one match, so the full binary certificate will be in that record type, or we can use the SHA-256, SHA-512, and DANE's RFC actually supports expanding algorithms. But the most interesting field by far is the certificate usage field. So what this field specifies is what kind of certificate are we going to be receiving, and how are we going to handle the certificate once we do receive it. So say we get a signature back for a certificate, and then we use the certificate usage of 0. Well, this is going to be a CA constraint, so basically this is saying that we specified the certificate of a PKIX approved, so be in your trusted store, certificate root. So we can say we don't want to use anybody other than VeriSignLabs.com for the certificate that you're about to receive. Similarly, if you specified 1, not only does the certificate have to be verified by PKIX, but we're saying that that exact certificate has to be the one that we received from the SSL cert. So even if it does verify, like goes through the PKIX checking and it's a legitimate certificate, it's got to be the one that we specified in that TLSA record type. And then conversely, 2 and 3 are similar, but the exact opposite. So we're saying that if we specify 2, it would be a certificate that gets verified as a trust anchor, but it doesn't have to be verified by public key infrastructure. So we could create an SSL cert that we then sign other certs for, and we could actually use that as our trusted CA, basically, without using an actual trusted CA. And then finally, 3, which we call kind of like cert pinning, is this is a certificate that you're about to receive, and it doesn't have to be validated by PKIX. So there's no reliance on public key infrastructure when you use certificate usage 3. So what does this kind of look like? Again, a Wireshark capture of the query. And like I said, you just so say we're going to make an HTTPS request to good.dane.verisignlabs.com along with like a record request for the IP. Then we would send a TLSA request to _443._TCP. the domain. And then what do you get in the response? Well, like I said, you get a few things. So you get the certificate usage, the matching type, and the selector, as well as the signature. So this right here, that 03, the thing that's highlighted, that's the actual SHA-256 of a record that you're about to receive from that HTTPS server. And then you'll notice also along with that, you've got the VeriSignLabs.com RRSig. So this TLSA record was just validated using DNSSEC. So how does this stop an SSL man in the middle? What this does is now, even if a SSL cert was compromised, we can now say through DNSSEC, we can verify that the certificate that was specified in that DNS request has to be the one that you're going to receive. You can't use any other certificates as long as that client is validating on DANE. So why am I kind of talking about DANE? What's the need for DANE? And there's a few problems with the CA system. But first I'm going to just start off with a couple of examples that I think really highlights the problem. The first example is DigiNotar. In July of 2011, an attacker was able to compromise DigiNotar and was able to create wildcard certificates for anybody. So they created it for Google, and then they used that to man the middle Gmail for about 300,000 Iranian users. And then during that time, they were also creating wildcards for Yahoo, Mozilla, WordPress, and numerous other sites. So notice these dates. In July of 2011, this happened. In August 29th of that year, Microsoft finally revoked that certificate using CRL. Another example, DigiCert Malaysia, not to be confused with DigiCert, the US provider, two separate entities. They were an intermediary CA for Entrust. And on November 3rd, they started releasing really poor quality certificates. So they were like 5 12-bit RSA keys. They didn't have a lot of the things that are required by SSL certs, and they were giving them to the Malaysian government. And it was realized on November 3rd. Mozilla finally used revocation on November 17th, so about 2 weeks before they were able to actually even push out the revocation. So what do these two events kind of signify? Well, one, a compromise in the chain completely compromises the entire chain of trust. If DigiCert's compromised, then not only is the SSL certs that DigiCert has already signed compromised, but the entire system is compromised because they're a root CA. We've completely trusted them for the security of, say, our HTTPS traffic. And then also, once a compromise has happened, it's incredibly difficult to revocate that because of the way that our revocation system currently is. And DANE is perfect for fixing both of these issues. One, pinning on the DNS completely eliminates the need for a CA system. Like I said, we can actually pin on an SSL cert. And now that we control, our organization owns that DNS server, we now own the security for, say, our HTTPS traffic. And then also, it handles revocation really elegantly. And it's kind of a side effect that no one's really talking about right now, but it's, I think, something that's really good to be noted. Speaking of revocation, how are we doing revocation right now? And really there's two answers. There's CRLs and OCSPs. CRLs are basically a list that gets pushed out, specifying which SSL certs have been compromised or rolled out or no longer valid. And it's too large. There's no way it's scalable. It's a huge list. And so because it's too large, they got to cut out like a bunch of them, and it's not comprehensive. And also, if we don't get this list, we can't just shut down our CA checking system because, like, if you DDoS a CRL server, then it would just take down the entire internet, or at least all secure internet. And then similarly, OCSP, this is more of a receiving a CA signed cert. It checks to see if it's a valid certificate. And again, they've got issues with, like, you're constantly going to OCSP servers to check for certificate validation, and again, it's a fail-open system. So, like I said, we're going to talk about some Heartbleed here. So, an interesting consequence of Heartbleed is that everybody thought that their CA cert was compromised, and then everybody wanted to revoke their certificate and publish a new one. But there's just really no way of handling this currently. Adam Langley from Google basically specified that Chrome uses a mixture of CRL and OCSP, and neither one of them can handle revocation properly or significantly enough to revoke mass amounts of certificates. And DANE handles this really well. So, say your certificate gets compromised. Well, now all you do is, create a new certificate, push it up to the HTTPS server or whatever server, and then simply update your DNS record with the signature of your new certificate. And now you're pinning on a completely separate certificate, and if anybody uses that compromised cert to try and man-in-the-middle your connection, it won't be valid because the TLSA record type takes care of that. So, yeah, we have these problems with CA cert, but there's also problems with the DNS server. So, with their CA system, it's not really any longer a chain of trust, it's more of a web of trust, just because there's so many intermediary CAs out there and any one of them can get popped. Whereas a DANE DNS connection is more of a tree of trust. DNSSEC, your either yours or your .com or your root has got to get compromised to compromise your DNSSEC traffic. And and then there's some other issues with with your CA system. We have multiple root trusted CAs, whereas this one only uses one, and that's the government. So that's really kind of a pro and a con, depending on how you look at that. The people that run those CAs are multinational conglomerates. Symantec, Komodo, GoDaddy, GlobalSign, those are the big ones. Versus this one's going to be owned by IANA, and then the people that own those TLDs. And then that's going to kind of change when we have all these generic TLDs coming out, because now we're going to have a lot of different separate companies that are going to be able to publish DNSSEC validated records. So that's going to be something to watch out for. And then protections in the SSL handshake. At least with the CA system, it's all in one protocol, right? It's all in the SSL protocol, whereas now we're kind of breaking it out into a second protocol to handle this. So there's some introduction of some more attack surface by using two protocols instead of just one to validate our SSL traffic. And then, something to look at is, how many CAs have been compromised versus how many DNS servers have been compromised. And if we decide to move towards a more DNS-based approach to security, I definitely think that we're going to start seeing a lot more DNS compromises, but there's already been some significant ones. Just take a look at MS 11058, huge compromise in Microsoft's DNS. So luckily you don't have to choose though, because like I said, with the certificate usage, we could actually pin not only using TLSA, but also using your CA, using certificate usage 1, which basically says this certificate has to be validated by PKIX, but it also has to be the certificate that we specify in this TLSA record type. So I'm starting to run out of time here, so I'm just going to jump over that. Again, we have this issue with implementation, and this is going to be. It's because it's a bootstrap protocol, right? So no one wants to implement DANE, no one wants to implement DNSSEC because it's a protocol that no one uses. And no one uses it because no one implements it. So there's kind of the chicken or egg situation. And, like I said, 0.3 of .com uses DNSSEC, and like a handful of sites use DANE right now. There's a really good tool out there called DNSSEC Validator that will actually check for TLSA records as well as DNSSEC. So check that out if you're interested in actually using that for your client. There's a couple of good sites that you can actually test that out on. I've got dane.tonycargile.com. That is validated by TLSA record types, as well as good.dane.verisignlabs.com. And also, if you want to check out if your validator is working, there's bad.dane.verisignlabs.com as well. So one of the reasons I took a look at this was because of NCC Domain Services. NCC is the parent company for ISEC partners, and they're actually releasing this new TLD called .trust. And what it basically does is it requires that anybody in that TLD to get regular penetration testing, and they have to comply to a rigorous set of standards to be in the .trust TLD. And one of those standards is that they have to be using DANE, and they have to be using DNSSEC. So I think this is a really great sign that we're going to start seeing this a lot more. There's a reason why people are talking about this a lot more. It might not be implemented yet, but it's good to start talking about this and start looking at the security of this before it gets implemented. And kind of going with that, what can you do? I think there's 3 different ways of looking at what can you do if you actually believe in DANE or DNSSEC, and that's builders, breakers, or handshakers. If you're a builder, obviously this kind of applies to you. If you're a web server maintainer, why not sign your zone with DNSSEC? Or if you're an application developer, why not build into your HTTPS stack validation for DANE? Also, breakers. So this stuff definitely is going to need testing, right? So we're building new code It's using crypto, so it's probably going to use C or some native language code to write the validation for this DANE and DNSSEC, and we're going to start putting this in a lot of different clients if it picks up. So, and already we're kind of starting to see that. A recent, in 2013, there was actually a arbitrary remote code execution in GNU TLS in their DANE validator. So I think for people like me that get paid to just break things, I think we're going to see a lot of issues with breaking things in DANE and DNSSEC for developers that aren't paying attention to this new code. And finally, handshakers. Like I said, no one's adopting this right now, and it's going to take some pushing from IT, pushing from an organizational standpoint to finally get DANE and DNSSEC into Google, into any of your Alexa top 25 or top 100. We need to start communicating with upper management that this is why we need DNSSEC, and this is what it'll provide for our organization. So I kind of rushed through that last bit because we were kind of running out of time. I want you guys to be able to get to lunch here. But do you guys have any questions about what I just went over? Yes, with that.
Yeah, so I have two questions. One, you mentioned a handful of people were using DANE. Do you know, close to the numbers, whatever, you had, the percentages for DNS?
We're talking maybe 10. I mean, this is very low. I don't know the exact number, but it's enough to tally,
Cool. And then, I'm a huge advocate of SSL pinning and stuff like that. What are some of the hurdles to keep all of the signatures that you're keeping in the DANE server, the SSL certificates, up to date, right? So that when you actually do that SSL certificate pinning, that those are actually correct.
Yeah, so that's a big, a lot of people like to complain about, well, there's some standards for, how long do you keep your zone signed for, how often do you re-sign, that kind of thing. And in the RFC, they kind of specify using an HSM to be able to hold your keys off the server, and then you can use some sort of automated pooling of that aspect, but that's going to be more of an organizational decision. But kind of going with that is that Bind has now released a set of tools that really makes it really easy to re-sign your zone and to do key rotation. So those solutions are becoming more available. The larger that DNSSEC and DANE get, there's going to be more availability of that tools, but right now it is kind of limited. And that's a big negative that a lot of people don't want to have to hassle with having to rotate another set of keys. Any other questions? Yes?
So at one point Chrome had support for DANE. Do you have any insight of why?
So yeah, I mentioned Adam Langley in this talk, and he's got a pretty good post on that about why it was in Google and why they took it out. But really, what it boiled down to was no one was using it. You can actually get forks of Chromium that still support it. Basically, they just took that code, put it in Chromium forks, and you can use that. But that's the reason why. At least that's what Adam Langley says is the reason why they took it out of Chrome. Any other questions? All right, thanks everybody for coming out. I really appreciate it.